In mathematics, an autonomous system or autonomous differential equation is a system of ordinary differential equations which does not explicitly depend on the independent variable. When the variable is time, they are also called time-invariant systems. Many laws in physics, where the independent variable is usually assumed to be time, are expressed as autonomous systems because it is assumed the laws of nature, which hold now, are identical to those for any point in the past or future. Autonomous systems are closely related to dynamical systems. Any autonomous system can be transformed into a dynamical system using very weak assumptions. A dynamical system can be transformed into an autonomous system. Definition: an autonomous system is a system of ordinary differential equations of the form where x takes values in n-dimensional Euclidean space and t is usually time. It is distinguished from systems of differential equations of the form in which the law governing the rate of motion of a particle depends not only on the particle's location, but also on time. Such systems are not autonomous. Properties: let be a unique solution of the initial value problem for an autonomous system, then solves. Indeed, denoting we have an. Thus, for the initial condition, the verification is trivial. Example: the equation is autonomous, since the independent variable, let us call it, does not explicitly appear in the equation. To plot the slope field and isocline for this equation, one can use the following code in new Octave. MATLAB FFUN equals at *y% function f equals y, x, y equals mesh grid, %choose the plot sizes dy equals FFUN, dx equals 1s, %generate the plot values quiver, %plot the direction field in black, hold on, contour, %add the isoclines in green, title equals y. One can observe from the plot that the function is invariant, and so is the shape of the solution, i.e., for any shift. Solving the equation symbolically in MATLAB, by running y equals d solve *y x, %solve the equation symbolically, we obtain two equilibrium solutions, and a third solution involving an unknown constant, y equals -2, 1. Picking up some specific values for the initial condition, we can add the plot of several solutions. y1 equals d solve *y, y equals 1, x, %solve the initial value problem symbolically, y2 equals d solve *y, y equals 1, x, %for different initial conditions, y3 equals d solve *y, y equals 1, x, y4 equals d solve *y, y equals 3, x, y5 equals d solve *y, y equals 3, x, y6 equals d solve *y, y equals 3, x. EZ plot, %. Plot the solutions EZ plot, title equals y, legend, text, grid on. Qualitative analysis. Autonomous systems can be analyzed qualitatively using the phase space. In the one-variable case, this is the phase line. Solution techniques. The following techniques apply to one-dimensional autonomous differential equations. Any one-dimensional equation of order is equivalent to a dimensional first-order system, but not necessarily vice versa. The first-order autonomous equation is separable, so it can easily be solved by rearranging it into the integral form. Second-order. The second-order autonomous equation is more difficult, but it can be solved by introducing the new variable and expressing the second derivative of a so that the original equation becomes, which is a first-order equation containing no reference to the independent variable, and if solved provides us a function of. Then, recalling the definition of, which is an implicit solution. Special case. X equals f. The special case where is independent of benefits from separate treatment. These types of equations are very common in classical mechanics because they are always Hamiltonian systems. The idea is to make use of the identity which follows from the chain rule. Note aside that by inverting both sides of a first-order autonomous system, one can immediately integrate with respect to, which is another way to view the separation of variables technique. A natural question is then, can we do something like this with higher-order equations? The answer is yes for second-order equations, but there's more work to do. The second derivative must be expressed as a derivative with respect to instead of. To re-emphasize, what's been accomplished is that the second derivative in has been expressed as a derivative in. The original second-order equation may then finally be integrated. This is an implicit solution, and beyond that the greatest potential problem is inability to simplify the integrals, which implies difficulty or impossibility in evaluating the integration constants. Special case x equals x nf. Using the above mentality, we can extend the technique to the more general equation where is some parameter not equal to 2. This will work since the second derivative can be written in a form involving a power of rewriting the second derivative, rearranging, and expressing the left side as a derivative. The right will carry plus or minus if is even. The treatment must be different if higher orders. There is no analogous method for solving third or higher order autonomous equations. Such equations can only be solved exactly if they happen to have some other simplifying property. For instance, linearity or dependence of the right side of the equation on the dependent variable only. This should not be surprising, considering that nonlinear autonomous systems in 3 dimensions can produce truly chaotic behavior such as the Lorentz attractor and the Rossler attractor. With this mentality, it also isn't too surprising that general non-autonomous equations of second order can't be solved explicitly, since these can also be chaotic.